Does anybody have any questions before we start?
I do.
Yes.
Does anyone want food tonight? Well, that's very good. Because I'm gonna want food. Maybe is that like four people? What are you thinking? Pizzas. Yeah.
Did you get the answer you need?
We'll check back in an hour.
Okay, sounds
We'll
good.
see how they're
15
doing.
minutes from now, we'll be back.
Yeah, we'll see how they're doing.
Okay, today I'd like to start talking about a different way of enhancing gain with cascaded amplifier structures. So a review from last time, we compared the gain of a current mirror op amp with the reference op amp, and we initially saw that in the small signal parameter domain, it appeared to give us a gain increase of M, which is the mirror gain, and it appeared to give us an increase in the gain bandwidth product factor of M. And that looked really good. Mr. Kimmler asked some questions about whether that was really as good as it looked, and we found out that it wasn't. In fact, what we found out was that if you compare things fairly, what do we find? We found that the gain expression was exactly the same as what we had before with the reference amplifier. So we gained nothing from a DC gain viewpoint, as if it had the same VXS bias voltages. And as far as the GB is concerned, we found things actually got a little bit worse. This was the expression that we had previously. It was this term here, and this is multiplied by M over 1 plus M. If M is around 1, so the mirror gain is 1, it costs us twice as much power with this amplifier as it does with the reference amplifier. Okay? So that was a little bit disappointing. Now, one thing I didn't do a good job of yesterday was when I compared this structure with what, I guess first of all with the current mirror biasing. So if you look at the structure here, this has a single-ended output here. So what we're doing is we're taking the signal on the left here, and we're mirroring it through M5. No, not this one, excuse me. So I'll do this wrong again. So this is with the constant current source bias. And then the other thing we did was put, do I have the mirror on the bottom? No, I didn't have the right slide. So if we want to convert this structure to a current mirror on the right side and lose this one output, we take this terminal here and just tie it around to this point here. At that point, we have 3 mirrors. We have a mirror on the top, on the right, a mirror on top on the left. This signal on the left here will get mirrored to here, doesn't go to the output, then it gets mirrored through the M9, M8 mirror back into here. So basically then we have 2 currents coming here in the output, one coming from the right side of the circuit, from this current mirror, the other coming from the left side of the circuit. If the mirror gain, the product of this mirror gain and this mirror gain is the same as this mirror gain, then the signals coming from the top and the bottom will be the same, but they'll be 180 degrees out of phase. So that will double the signal-dependent current that's driven to the output node. Okay, so it's a fairly clever structure that they have for going to a single-ended output on this. The other thing I didn't do well on the last lecture, I skipped over the section of modifications of the circuit to have slew rate enhancement. I made a comment, here's some slides on slew rate enhancement, and I just went past them. Your author talks about the benefits of that slew rate enhancement architecture that's in the slides. The slides will be posted. Actually, there's no benefit to enhance slew rate structure. If you go back and compare in the practical parameter domain, you'll find that the slew rate is actually a little bit worse than it is for the reference object as well. So that's what I did not talk about previously. We also looked at a different perspective for the structure. We looked at trying to redraw this circuit here, and we saw that it was really a cascade of two amplifier stages, both common source amplifiers, one with N-channel inputs and one with P-channel inputs. And so that was actually a cascaded structure. Of course, we got the same gain expression we had before, just looking at the circuit in a different way. And this was a summary that says the current mirror op-amp will work. It's a relatively clever and simple structure, but it does not give us much improvements in performance. If you have a fairly high mirror gain, the improvement's about the same as what you had for the performance, about the same as what you have for the reference amplifier. If the mirror gain is small, you have close to a factor of 2 degradation in performance. We also talked about stability. And the reason we're starting to talk about stability now is because we're going to start looking at two-stage amplifiers, and those two-stage amplifiers will have a stability problem if they're not careful. So we want to be rigorous about defining stability. Now, I'm assuming everybody understands stability very well, so I could ask people to raise their hands if they understand stability very well, and then we could skip over these slides. But if you want to have a discussion of stability again, it's important to really understand it well. I'll go through a little bit of a review. How many people feel they understand stability very well?
Define understand stability well.
Yeah.
It's easy. We'll change seats.
Yeah.
Pardon?
Can you go over the review slides?
I think it would, regardless of what we think about it, I think it's still useful to see it in the context of analog integrated.
Good answer.
Yeah.
Okay, that's fine. Well, I'm glad you didn't. I'd be glad to take you up on it, actually. But if you would have said you don't want to see it, I'd be dancing for the next 40 minutes.
Oh,
Well, in that case.
The poles of an amplifier are the roots of the denominator polynomial of the transfer function. We talked about that. We said that energy stored, the number of energy storage elements, that is capacitors and inductors, determine the number of poles we have in the system. As long as you don't create capacitor inductor loops, and for each loop you reduce the number of poles by 1. The poles of an amplifier can often be approximated by independently considering the impedance facing each capacitor and assuming all of the capacitors are either open circuits or short circuits. We will go through that in a little bit as well. We talked about a dead network. Dead networks, a circuit can be obtained by setting all independent sources to 0. The characteristic polynomial or the poles are absolute. They're inherent in the dead network. So basically, we can make the statement, if you give a given circuit, we can talk about what the poles of that circuit are, independent of where the excitation is applied and where the response is taken, assuming that you compare them with the same dead networks. So any two circuits that have the same dead networks will have the same poles. Zeros is a different story. The zeros could be entirely different. Zeros are dependent on where you apply the excitation, where you take the response. That seems like a pretty powerful observation that the poles are the same irrespective of where you take the output. You can take any current output on a circuit, any node voltage output, any differential voltages on the circuit at the output, divide that by any input, and the poles will always be the same. Can somebody give me an argument as to why the poles of a network will always be the same, irrespective of where you take the output and where the input comes from?
You always have the same number of storage elements in the network.
Okay, so the order is the same.
Yeah.
There's a big difference between saying the order is the same and saying the poles are all the same. We're certainly not going to exhaustively look at all transfer functions of a given circuit. If you have a circuit with 3 capacitors in it and half a dozen resistors and maybe 8 nodes, we could have dozens of different transfer functions for that circuit. And if we did that, all of them would have the same poles. What? Do you believe it?
I mean, they're saying that. I wouldn't have thought that.
Yeah. So it's nice to ask the question, why? And to get some intuitive feel for why something so powerful as that observation applies. We'd have a problem if it wasn't true. Because if you had a circuit, and depending where the input was at, or where the output was at, in some cases it was unstable and looked like an oscillator, in other cases it was stable, then what's going to happen on all the node voltages? Are they going to be going up and down if it oscillates, or are they not going to be going up and down? Make sense? So there would be a concern if stability was not an absolute criteria. But why can we argue that the poles are all the same? Any ideas? So I'm going to give just a plausibility argument, and it could be made rigorous. If you take a circuit, you could write a set of equations of this form. You have an admittance matrix Y times the node voltage, if this is node voltages, so I'm going to assume that any of the outputs are node voltages right now. So this is a node voltage vector. And if I apply Kirchhoff's current law to every node, I'll get an equation, and this is equal to some excitation matrix. This is the form that we have for the nodal equations for a circuit. This is a vector of all the node voltages in the circuit. So I want to solve this circuit, I need all the node voltages. So I can say the node voltages are equal to Y inverse, I have to multiply on the left side, Y inverse times the excitation vector. Okay, that gives me all the node voltages. Now, if I want to look at Y inverse, Y inverse is obtained by a ratio of two determinants. One determinant is in the numerator, and what you do is you replace some column in that vector. Let me do it differently now. Let me look at some voltage here, VK, one of the voltages here. And so what you do is you take this matrix and you look at a determinant, and the determinant is obtained by replacing, I believe it's column K, by the excitation vector. And the rest of the entries in this determinant are the Y matrix values. Divided by the determinant of the matrix, of the indefinite matrix Y. Y11 through Y1n, Yn1 through Yn. Okay? So the voltage Vk for any node is the ratio of two determinants. So notice that if I want a different output, I just replace the excitation vector in a different column in this determinant. What have I done to the denominator? For different outputs. Stays the same. That denominator gives us the denominator of the transfer function. Okay? So this is a plausibility argument. It can be made rigorous. But we show then that all of the node voltages have the same denominator polynomial. Hence, the difference of two node voltages have the same denominator polynomial. Hence, any current, which is going to be a branch voltage divided by an impedance, has the same denominator polynomial. Hence, all denominator polynomials for any transfer function of that network are the same. Make sense? Okay. How many people knew that? Kind of.
It has something to do with state, like there's one unique state space, and then you have all these different transfer functions mapped to one of them.
I suspect that's the same issue. That's correct. You studied that in the controls course?
Yeah.
Okay. Let's talk about two-stage op amps. So the current mirror op amp we saw was a cascade of two amplifiers when we looked at it in an older perspective, and the gain was a product of the two. But for the current mirror op amp, A1 was much, much less than A2. The gain on the first stage was a common source amplifier driving a diode connected transistor. So that was a low gain stage, followed by a high gain stage. So we asked the question, could the gain be increased by cascading two or more amplifiers if the amplifiers have a higher gain? That's the way you get the gain to go up. So instead of having A1 much, much less than A2, let's have them both be high gain amplifiers. Now we get some real improvements on our gain. So again, I'm going to assume the stages are non-interacting. The gain is the product of the two gains, or if there's three, the gain is the product of the three. If there's n, the gain is the product of n stages. So we can get the gain up to an arbitrarily high level just by adding more stages. And it's easy to do it. You could just copy and paste. And if you got a gain of 40 dBs on one stage, put two together, you got 80, put three together, you got 120, put four together, you got 160, and so forth. Right? Easy to do. But each of the gains will roll off with frequency. So we can model each of the gains as a DC gain, A0K of the K stage, divided by S over PK tilde plus 1, where PK tilde is the negative of the pole of that stage. Thus, the overall gain is the product of the AIs over the product of S over PK tildes plus 1. Of course, at DC, the PK tildes become 0, or the S comes 0 in the denominator, and we see the DC gain is just a product of the DC gains. If you look at the magnitude of the gain, if each of the stages rolls off at 20 dB per decade, that's what happens if you have a single pole amplifier, and the phase shifts 45 degrees at the pole, and it moves down to 90 degrees. If you cascade a number of stages together, the gain falls off at 20 n dBs per decade, and the phase shifts to minus 90 n, where n is the number of stages in that structure. That still looks pretty nice. We can get a lot of gain up to high frequency. In fact, we start to get almost an ideal low-pass filter. Amplifier acts like an almost ideal low-pass filter. It cuts all the noise and everything off at high frequencies past that pole. Yes?
In the multi-stage case, the cutoff frequency is at which point? Like there it is at P, there it is at P.
Okay, so if you look at the 3 dB frequency, the 3 dB frequency will just be slightly less than P. Because if you look at P, each one is going to be down 3 dBs. So if you're 3 stages, you'll be down 9 dBs at this frequency. So if you back off just a little bit to the left, you'll be 3 dBs down. So the 3 dB bandwidth is just slightly less than the original pole frequency.
Of the first stage.
Yeah, right. They're right now, well, if the stages are all the same, it'll be just less, a little bit less than that pole frequency. Okay. Much larger gain, much steeper transition, and much more phase shift. But we don't use the op amps open loop. We use them closed loop. So let's assume that we put them in a configuration that can be represented with the standard feedback model. So the gain with feedback is A over 1 plus A beta. So if I take this configuration, the non-inverting amplifier, V out over Vn is equal to 1 plus R2 over R1 divided by 1 plus R2 over R1 divided by A. As A goes to infinity, it reduces to 1 plus R2 over R1. It happens that if you multiply by A, the beta is the reciprocal of this term here. So this is the form A over 1 plus A beta. I can draw that circuit like this. Here's the A amplifier. I'm sampling the output and putting into this resistive divider network, R1 and R2. I get a voltage here that's R1 over R1 plus R2 out. That voltage is in series with the input, but opposite in sign. The sum of those two go into the amplifier. So I've drawn this circuit on the top as a standard feedback amplifier per the approach of Black in the 20s and 30s. Okay. So the beta we said was R1 over R1 plus R2, and we get exactly the same gain expression as we did just analyzing it using Kirchhoff's laws. Next thing I'm going to do is then look at the feedback gain. It's A over 1 plus A beta. So if I put in a single pole amplifier model for the device, and I assume that the amplifiers are identical, I'm going to put in identical stages together. The gain with feedback is then A0 to the n, divide S over P tilde plus 1 to the n, plus beta A naught to the n. Why would I want to make the gains the same? About the easiest way we can do it, isn't it? Make them all the same, make them big, cascade them together, and we get this really big gain. We know that if we have a transfer function, then the roots of n of s are the zeros and the roots of d of s are the poles. And I've shown a pole zero plot here. I'm showing 4 poles in the left half plane and 1 0 in the left half plane. We might get something like that for a 4th order system. Theorem. A linear system is stable if and only if poles lie in the open left half plane. If a circuit is not stable, and a circuit is in one of 3 modes, it's either stable, or it's unstable, or the poles are on the imaginary axis. Stable poles in the left half plane, unstable in the right half plane. What do you want to define it as?
Marginally stable.
Marginally stable poles on the imaginary axis. Anybody else want a different definition for the imaginary axis? A different definition on the imaginary axis? Oscillatory. Any other definition? I don't care about a definition on the imaginary axis. Because imaginary axis is a set of measure 0. Nobody's ever built a circuit with a pole imaginary axis, and never will. You build a circuit, and the pole will be in the left half plane or the right half plane. So do we need to define something that never happens? So I won't define what the imaginary axis is, because you'll never put a pole there anyway. You have a pole that moves across it, maybe, but you can't build a circuit that the pole will sit there. A feedback amplifier circuit that is not stable is not useful as a standalone feedback amplifier. We saw examples earlier where a circuit that is unstable might be useful in some other circuit, like a filter circuit, but as a standalone amplifier with no additional feedback, it's not useful as an amplifier. A feedback amplifier circuit that is close to becoming unstable is not a useful standalone amplifier either. And I'm a little bit uneasy about using the term close to being unstable because things are either stable or unstable. So by close to being unstable, I mean an amplifier that has poles that are close to the imaginary axis in the angular sense. That is, the angle that the pole makes with the imaginary axis is a very narrow angle. An amplifier circuit that exhibits excessive ringing or gain peaking is not useful as a standalone amplifier. So if you take an amplifier and ideally in the frequency domain, an amplifier will come out someplace and go down like this. This is typical ideal closed loop response. Magnitude of A closed loop. And if you put a step input into the circuit, the output we would like to step up like this. But we could be in a situation where the output of the amplifier comes out and it does this. This is what we call peaking. This is gain, peaking. Or we could be in a situation where instead of the output looking like this, it looks like this. So the lower output shows ringing in the time domain, and the upper one shows overshoot in the amplitude domain. Both are usually considered to be undesirable. Okay? So this structure here, if you have these poles, is stable because it has two negative real axis poles and two left half plane complex conjugate poles that are not real close to the imaginary axis in an angular sense. This pole here could be close to the axis in the magnitude sense, but it's not close to the imaginary axis in angular sense, so it probably doesn't cause us a big problem. Here's another situation. Now we have a pole in the right half plane, so this amplifier would be unstable because of the positive real axis pole. Here's stable with negative real axis poles. Some of the amplifiers we build will intentionally put the poles in the negative real axis. Here's a structure that has complex conjugate poles. If you look at a structure with these poles, the output will oscillate. If you have a pole on the positive real axis, the output will saturate. We'll talk about why that happens shortly, just to review that as well. Here's a situation where we have stable because the poles are in the left half plane, even on the negative real axis. We have a zero in the right half plane. Zeros play no role in stability. In fact, oftentimes we'll design circuits, so we intentionally put the zeros in the right half plane. So the system zero locations have no impact at all on stability. Here's a situation where the poles are close to the imaginary axis in the angular sense. So this is close to becoming unstable since the poles are, in the angular sense, are close to the imaginary axis. So let's look at practical implications of stability or coming close to being unstable. So if I take any linear system, the response to an excitation xn of S can be written as the product of xn of S and the transfer function. And I can expand the output in a partial fraction expansion. That's of the form summation k goes from 1 to n of ak over s plus pk tilde, where the pk tildes are the negative of the poles of the amplifier, plus the summation k goes from 1 to h, where h are the number of terms in the denominator of the excitation, times bk over x plus xk. And the xk's are the negative of the roots of the denominator of the excitation. If pk is the negative of any pole, and that's how we define the pk, then pk can be expressed as minus alpha k plus j beta k. So the pole has a real part and an imaginary part. So then the pole is actually at alpha k plus j beta k. Real part is alpha k, imaginary part is j beta k. If there's a pole in the right half plane, one of the alpha k's at least would be negative. If all the poles are in the left half plane, then all of the alpha k's will be positive. Beta k's may be 0 or non-zero. So we take the inverse Laplace transform to find the output in the time domain. And all we have to do is sum the outputs of each of that terms in that partial fraction expansion. So the output in the time domain then is the inverse Laplace transform of the excitation times t of s. So it'll be some k goes from 1 to n of ak e to the alpha kt e to the j beta kt. This is the output that's due to the transfer function, plus an output term that's due to the excitation. Thus, for the output to be bounded for any input, so another definition of stability is the output will be bounded for any bounded input. Thus, for the output to be bounded for any input, we must have all alpha k 0, less than 0. If any one of the alpha k's is not less than 0, we'll have a growing exponential term that will bound. If you look at this term here, this is a sinusoidal term. So you'll have a growing exponential bounding sinusoidal term. Only if all of the alpha k's are negative will you have a sinusoidal term, which is a step response, being bounded by a decaying exponential term. And that means that the transient response will always go to 0. We don't have to worry about this term here because we're assuming we have a bounded excitation being applied. So this is not going to force an output to go to infinity. So if we say the system is stable if and only if any bounded input results in bounded output, that's equivalent to saying that all poles have to lie in the left-half plane. If you have a pole is in the right-half plane, the output for any input, no matter how small, there will always be this part here due to the poles, and that will cause the output to diverge to infinity. If the beta k is 0, which would correspond to a pole on the positive real axis, this term is gone, and this becomes just a DC term. If there's complex conjugate poles in the right half plane, there will always be a sinusoidal growing term. So poles on the positive real axis don't cause oscillation, they just cause growing exponential. Of course, it only grows until an electronic circuit saturates, and then it climbs. It becomes nonlinear. Any questions? Yes.
When manufacturers say that this model of an op-amp is improved latch up, or you know what I mean, like the latch up rate or what, I don't know how they quite phrase it, but are they just saying, is it with this context, or is it that is there such a thing where the circuit breaks beyond, I don't know, like suppose you overpower it or something, and then no matter what you do to the circuit, it's just stuck? Because I might have opened the door I didn't want to open.
Yeah, you open up another door. I'm not prepared to, well, I can tell you what goes on. If you look at linear models of an amplifier, latch up's not an issue. If you have an amplifier, they design it so the feedback poles are well positioned in the left half plane for appropriate value of beta. But you have a nonlinear system. And occasionally what you will have is feedback in that operational amplifier that will cause that nonlinear system to do one or two things. It will break into some form of oscillation, oftentimes non-sinusoidal, or the output will just get stuck at some point. Completely unpredictable by the small signal model. You're not a good op-amp designer if you design circuits that have that problem. Unfortunately, that problem is associated with two things. It's associated with how you design the op-amp, and it's associated with how the customer applies the op-amp. So you may be a good op-amp designer, and if some customer's application has a latch-up or a sustained oscillation problem that's not small signal based. A number of years ago, I used to work in the filters area, and I had this filter I thought was pretty good. And I built it in the laboratory. Actually, I had a laboratory set up in the back of my office, and I had this filter turned on, and I was watching it over an extended period of time. I'd come every morning, and the filter was working fine, the filter was working fine. One day I walked in and it was oscillating. And The reason I left it on a long time because I had seen that pop up accidentally one time when I was playing with it. Every once in a while it jumps to this mode of oscillation. And the only way I could get it out of that mode of oscillation is to turn it off and turn it back on. About a year later, I was at a conference and somebody was presenting a paper. Coincidentally, it was that same circuit. And that circuit had really nice performance when it's treated as a linear amplifier. So I asked the speaker if he had ever any problems with the circuit jumping into oscillation. And he reacted about like I did when you asked the question. And he said, let's talk about that offline. And he said, yeah, it happened. And I said, what did you do about it? He said, well, I rebuilt the circuit. And as soon as I measured results, I turned it off. So I can point you to the literature where circuits exist, where the author knew that there was a problem and had a paper published and said all kinds of good things about a circuit that's completely useless.
Sun's blowing through.
So be careful.
So let's look at the situation now where we have just three stages. Identical. So if with three stages, the gain with feedback is going to be then A naught divided by S over P plus 1 cubed plus beta A naught. Now, even though it's a third order polynomial, I made a statement that it's hard to get a general solution for a third order polynomial. That doesn't mean it's always hard to get solutions for some third order polynomials. This is a third order polynomial we can solve. So if I set the denominator polynomial equal to 0, I'm going to get S plus P tilde cubed. I'm going to get S over P tilde, plus 1 cubed plus beta A naught cubed equal to 0. I can solve that equation for the poles, right? So then I can say S over P tilde plus 1 cubed is equal to minus beta A naught cubed, or S over P tilde plus 1 is equal to the cube root of the right-hand side, and the cube root of the product is the product of the cube root, so it's minus 1 to the 1/3 times beta to the 1/3 times A naught, or S over P tilde is equal to minus 1 minus plus minus 1 to the 1/3 beta to the 1/3 A naught, or finally S is equal to P tilde, which is positive, times minus 1 plus minus 1 to the 1/3 beta to the 1/3 A naught. So I've got a closed form expression for the poles. How many poles do I need? 3. If I look at this expression, I've written it right here, and of course, I have a 1 plus beta A naught that's about beta A naught. It's about minus 1 to the 1/3, beta to the 1/3, A naught times P tilde. Where do I get the 3 poles? Where do I get the 3 poles? Garrett.
You have 3 same roots.
What? That 3 roots are the same? No. There's only 3.
There's a -1 and then there's a complex pair in the right half plane.
Yeah, there is, but how do we see it?
That's the -1.
Right. -1 to the 1/3 has 3 values. The cube root of minus 1 is triple value. So those triple values of the cube root of minus 1 will give us the 3 separate poles. And here they're at. The magnitude of the poles are beta to the 1/3 times A naught times P tilde. So we know the radius here. And they all have a circle. So we see there's 2 poles here and 1 pole here. Good news or bad news? Bad news, this is a game of feedback. Open loop amplifier had 3 poles in the left half plane. It was rock solid stable. Try feedback to the circuit. And we see there are 3 poles, irrespective of beta. For any value of beta, we've got 3 poles, 2 of which are in the right half plane. So the amplifier is unstable. So let's look at how we might be able to have a denominator polynomial and determine if an amplifier is unstable. Because it's not a lot of fun to find the roots of a polynomial. If we have a third order polynomial in general, I was able to solve this one. But I can write down third order polynomials pretty easily that you can't easily solve. All I have to do is let those 3 roots be different. If you want to do P3 be different, if you want to write down the expression for those 3 roots, it'll be 2 pages in 6-point font for each of them. Are you with me? Okay. So is there a way we can determine if an amplifier is stable without going and finding the roots? How many, is everybody familiar with Rauth-Hurwitz criteria? Everybody's familiar with it? Okay. So anyway, if we have a third order polynomial, all we have to do is look and see if all the coefficients are positive. I've written an integer monic form, so this lead coefficient is 1. If all the coefficients are positive, and if the product of the inner 2 terms is bigger than A0, then the poles are in the left half plane and it'll be stable. Of course, we want a lot more than stability when we're building an amplifier, because we said if an amplifier happens to have poles that are close to the imaginary axis in an imaginary sense, it's still not a good amplifier. So this is a long ways away from being sufficient for telling whether we have a problem with an amplifier or not, but it is a way to tell that the amplifier won't oscillate. So let's consider the denominator polynomial and apply Rauth-Hurwitz stability criteria. The product of the inner 2 terms, 1 over p tilde cubed times 3 over p tilde squared. Did I do that wrong? Well, I need to multiply through by p tilde cubed to get an interharmonic form. So this will be 3 over p tilde, and this will be 3 over p tilde squared then, when I multiply through by p tilde cubed. So this product here then will be 3p tilde times 3p tilde squared, has to be bigger than the product added to it. So I multiply through by p tilde cubed, I'll have p tilde cubed times 1 plus beta a naught cubed right here. Okay? This is Rauth-Hurwitz stability criteria. Well, we expect that we're going to violate this because we know this circuit has right half plane poles, right? But let's look at the stability criterion for the circuit. So if I look at this expression, I find out it's independent of p tilde. It doesn't make a difference whether the bandwidth of the amplifier is 1 radian per second or 100 kiloradians per second. The p tildes cancel. In order for this to be stable, beta a naught cubed has to be less than 8. If beta is equal to 1, how much gain can we get on these amplifiers if we want to qualify feedback and it's still stable? What? Less than 8. 2 would put the pole on the imaginary axis, right? So we have to gain less than 2. Well, that's a bummer. We're not going to get much gain by cascading 3 amplifiers together. Make sense? And if you want to get a reasonable gain, you can use Rauth-Hurwitz criteria in the following sense. If you grossly violate Rauth-Hurwitz criteria, oftentimes your poles are not even close to the imaginary axis. They're way in the right half plane. So we can argue that not only is the 3-stage amplifier unstable, it's far from being stable. Well, we saw that because we saw those complex conjugate poles way in the right half plane. Make sense? So this Rauth-Hurwitz criteria is useful in amplifier and filter design. We can easily determine if the poles are in the left half plane without finding the poles. Usually analytical calculation will do us. We can also write down Rauth-Hurwitz criteria for higher order polynomials. So if you want to look at a 4th order or 5th order polynomial, Rauth-Hurwitz criteria becomes a little bit tedious when the order gets much of that past 4. 4 is pretty manageable. 5 and higher, pretty nasty. Okay. Example. Assume an amplifier has transfer function that has a denominator polynomial that can be expressed in this form. Determine the maximum value of K that will result in a stable amplifier. This is a straightforward application of Routh-Hurwitz criteria. So we just take the product of the inner two terms, because it's already in integer modic form. 2K times 4 has to be bigger than 16, or K has to be bigger than 2. If K is bigger than 2, this will result in a stable system if it has this as the denominator polynomial. If n is equal to 3 and the stages are not identical, I can write the transfer function like this. And the denominator polynomial looks like this. This is what I said would be really difficult to find the actual poles of the system. The DC gain, of course, is a product of the 3 DC gains. So I'm going to write down Routh-Hurwitz criteria. I can write down Routh-Hurwitz criteria here from this form. That's not hard to write down. Now I'm going to assume that P1 is less than P2 is less than P3. And that's without loss of generality. I'm just going to order them this way. So I'm going to assume that P2 is equal to K2P1 and P3 is equal to K3P1. Okay. Then the Routh-Hurwitz criteria can be expressed like this. 1 plus K2 plus K3 times K2 plus K3 plus K2. K3 has to be bigger than beta A naught. Since for a good amplifier, the DC gain is going to be large, we can see that there's going to have to be one or both of these Ks have to be very large for it to be stable. Not just a little large. If A is 100,000, those Ks have to get really big to be stable. If the Ks get really big, it means you have a large separation of P2 and or P3 from P1. Make sense? To be stable, the Ks have to be big. They have to be real big. And they represent the separation from P1, which by definition is the smallest pole. We can view this problem as accumulating too much phase shift around the loop. We saw that phase shift got too big. It's that large phase shift that's causing these stability problems. For many years, there were seldom designs in industry that involved a cascade of 3 or more amplifiers because of the problem of solving this or satisfying this equation. In recent years, we've got some groups in industry that are building 3-stage amplifiers. They've got some fairly complicated strategies to be able to satisfy Routh-Hurwitz criteria. We will talk a little bit about that later. We have similar implications on an amplifier, even if it's not the basic voltage feedback amplifier. So this structure here, we're able to draw like this. This structure on the right, the basic inverting amplifier, which is more widely used and doesn't have a common mode input issue, it cannot be drawn as a voltage amplifier in this mode. The gain with feedback for this structure is actually this form. Notice that the denominator polynomials of these two amplifiers are the same. Well, the reason they're the same is the networks are the same. And the denominator polynomials determine the poles. These circuits have the same beta, the same dead network, the same characteristic polynomial, the same poles, but different zeros. For some AV, not for a single pole AV. And the denominator polynomial can always be expressed if I multiply through by AV and divide through by this. The denominator polynomial can always be expressed in the form of 1 plus A beta. where A is the open loop gain and beta is the feedback factor for that network. I promised to break at the end of 50 minutes. How are you doing on time?
You got like 20 seconds left.
We'll put it in the bank. Let's take a 5-minute break, and we'll pick it up from here in a few minutes.